So today we're going to do one last review. We're going to complete one last review of using acid and base and the kind of the concepts that we've laid down in order to pick the side of the equilibrium that will be favored based on the stability of ions, right? So we have these 4 rules. The purpose of these rules is so we should be able, by inspection, any acid-base pair, or comparing the relative strength of any 2 acids or any 2 bases. There's a mnemonic, or you have a formula now that lets you look at, inspect different ions and pick which of these will be more or less stable. From that picks the direction of an equilibrium. That picks which way it will move. So in general, equilibrium move from what to what? From what kind of stable to what kind of stable? Less stable to more stable. And what do we say about that in terms of strength? It moves from what type of species to what type of species? Strong to weak. Strong acid and base will lead to, force you towards the weak acid and base. The less stable species will give rise, or they'll move the equilibrium in favor of the more stable species. We had 3 ones we've discussed so far. Electronegativity. The electronegativity trend allows us to rank or compare what? If you had to sort of put it in your own words, what does this let you do? What kinds of ions are you comparing in this case? Charged species, but which ones? Like, how are they related? 2 charged species that are same row, right? We're saying some species where the formal charge sits on an element, in this case, let's say O-, versus charged species, element, where the whole point is they are both charged species. The formal charge sits on an element. The relationship between the 2 charged elements are in the same row. Nitrogen versus oxygen. Fluorine versus carbon. Sulfur versus what? What would be a good comparative? You had sulfur. What's another one that you might compare it against? Sulfur versus what, sorry? Chlorine, yeah. Could you do phosphorus? Yep, that's all good. Exactly. And what you'll notice is a lot of the charged species, they kind of group together. We're not really talking about charged species on the other side of the table, right? We're talking about things in this sort of top right-hand corner. We're not dealing with lithium, beryllium. Reason why, those are our, most of the time, those are cations, right? Those are counterions to usually charged species. So we're talking really about this sort of central part. It really limits, this is not some intractable problem with crazy different varieties. What you'll notice is it's actually a relatively small part of the periodic table we're considering. That's 1. 2 is polarizability. Polarizability allows you to rank what? What is it in your own words? This is comparing what and what? Say again? Vertical, but what about it? It's again, charged species. Formal charge sits on elements that are related in the same column. So this, the classic one, would be something like fluorine minus versus chlorine minus. Most important, we're talking about elements that are charged themselves, right? We're talking about the negative charge or the positive charge sitting on an element, not in a molecule that has these species. The charge is sitting on the element that we're comparing. So this would also be oxygen minus versus sulfur minus, or oxygen plus versus sulfur plus. The formal charge is on the element. We're actually sort of in this relationship. Those are our first 2. Now we branch, yeah, sorry.
If you have, like, so based on the polarizability trend,
Yep.
Sulfur minus would be more stable than oxygen minus?
Exactly.
Is it the same trend for a positive charge?
Yes, it is. So like in general, being polarizable is basically saying how do you as an element react to change. If you're polarizable, you go with the flow. You have the ability to sort of bend and shift your electron cloud to deal with charges negative or positive. Polarizable is just a good thing when it comes to charged species. The less polarizable you have, the more centralized that charge is. Think about it almost like, it's not quite, but think about it kind of like entropy. If you've got a lot of ways to spread out your charge, good thing. Fluoride, it's very electronegative. That's not bad. But having that charge localized on one atom is less stable than its comparative by going down that same trend. Fluoride will be less stable than chloride, than bromide, than iodide. As you get more sort of squishy, more polarizable, charge has more space to sort of spread out over. Last one we did was resonance. Okay, if you had to describe resonance, what is this like? What are we doing here, or how does this help?
How big the space is to spread out the charge among the pi bonds.
Exactly. How many atoms you can share that charge over. Think about it like polarizability, but it's polarizability over many atoms, right? You're actually changing the direct, like how far this charge can sort of spread out over the entire molecule. You're now using, instead of having charge sitting on an atom, you're having charge that's now delocalized over the entire framework of the molecule. A classic example. This would be a localized charge on oxygen. There's nothing I can do in terms of resonance. I have an sp3 center here, an sp3 center here. Oxygen is formally charged, negative, versus a carboxylate, the negative charge or conjugate base from a carboxylic acid. Here we have resonance. It's still oxygen that's negative, but oxygen negative has resonance structures that allows us to migrate or move this charge. I could use my two-arrow formulate notation to create a resonance structure that would look like this, where I'm physically migrating that charge to another whole oxygen, right? It's now in a different part of the molecule. The negative charge is spread out over many atoms. The more resonance structures I have, the more I can spread it out, the more stable something gets. What was the analogy for this? This is kind of like go to the gym, the spotter. Having a really good friend as a spotter that's actually doing a lot of the lifting for you. You're sharing the weight between multiple people. Last one we have now, number 4, is called induction. Induction is also like, in the same category as resonance. Remember, the first two, we're talking about stabilizing a charge that sits on a formal atom. These last two, resonance is a way of moving that charge over many centers, but the charge physically moves. It is actually localized. There's negative or positive charge somewhere else in the molecule because of this resonance contribution. Induction's not like that. Induction is another form of sort of support, but it's much more of the very good coach kind of support. Once again, if we're in the gym, you're sitting there on the bench, and you have a coach that's like, yeah, you can do it. Doesn't help so much. If you got a coach that's like, yes, you get in there, that's great, you can do this. That support that more inductive thing is helping gives you that extra little bit of boost, makes you feel better about yourself. At no point in your time is the coach ever helping. At no point in time is the charge ever over on your inductive group. There's no point where that induction actually holds on to those electrons. They're just helping as being kind of a buddy nearby. So the example here, the one we talk about in our slides, looks like this. Oh, sorry, we'll come back to that one. In inductive effects, we're transmitting charge through the sigma skeleton. Resonance is using pi. Induction uses sigma. We're using the single bond. And all we're really doing is having a very electronegative group nearby where a charge is. That helps to sort of, think about it like it polarizes the charge a bit. It helps to sort of draw on it. Again, it's moral support. The charge never sits on the electronegative atom. The charge never moves to the electronegative atom. There's no actual sharing of electrons. This is just somebody who's really, really enthusiastic and positive, but will not actually lend you any money. So what happens is you get something that looks like this. The point is the localized charge is now stabilized by having this group next to it, but the charge does not ever reside on these other centers. So look at these guys. We have a group of carboxylic acids. We have a group of conjugate bases. So first of all, if we have to apply something to talk about stabilization, am I looking at the left hand or the right hand? Do I look at the acids or the charged conjugate bases? Charged. We cannot talk about the acids as they are. They're neutral. Let's look at the charged species. Okay, what do you see about these charged species? What things about these charged species so far might help you. You should already identify a couple that all of them share. Yeah.
They all have a CL on them.
They all have a CL, that's true.
Varies in the range of like closeness.
Exactly. What you see here, the pattern, chlorine is close, chlorine is maybe a little further, chlorine is at the end. But what else? What else is in here? Yes?
They have the same resonance pattern?
They all have resonance, so they all have some kind of stabilization built in. Charges on oxygen, is already oxygen kind of electronegative? Yeah, but that's common. So what I'm saying here is if we went through our list, oh, oxygen is negative, oxygen is negative, oxygen is negative. I can't use electronegativity. These are the same element. That's not how I would look at this. Oh, but they all have resonance. Yeah, they all have resonance. I cannot differentiate them based on that. They all have the same number of resonance structures. That is not what tells me about just more or less stable. So if you keep going down the list, the one thing that's different is the position of where this chlorine sits. If you look down here, think of this end of the molecule, that's your negative charged bit. You've got a chlorine that's really close. It's only one bond away. Here, chlorine is 2 bonds away versus 3 bonds away. The proximity of that chlorine is changing. It's getting further away. So, analogy of the coach or a friend or somebody who's helping you out. What's better? Up close, helping out, I'm right here with you, versus you can do it. The further away you get, the less help it can provide. So based on that, which is most stable? Top, middle, bottom? Bottom, that's right. The most stable ion here will be this one. It's the most stable because they all have an electronegative chlorine that is close by, in this case, versus middle versus far. The further away we get, the less it helps. Okay, so if we said this is most stable, let's go to this side. Who's the most acidic, top, middle, or bottom? Talk to each other. Get this right. This is something we finished, talked about. We have a couple mnemonics. I want to make sure you guys are solid on this. Sorry.
How do you know that like chlorine is the atom that can like do whatever
The electronegativity. If you look at the induction, so first of all, if you look between each of these, and I'll discuss it with the class, this is a really good question. If you look between each of these, the only thing that makes them different is they all have carbons, oxygens, chlorine. The position of that chlorine is the thing that you would sort of jump out. So that's where your eye should go to. Okay, what is chlorine? It is an electronegative atom. It is more electronegative than hydrogen. It's more electronegative than carbon. Those are the other.
So if it's also electronegative, it can kind of share the burden.
Yes. So being electronegative here, what we're doing is we're saying something like a chlorine or a fluorine or an iodine. These are more electronegative than carbon on their own. They're part of the skeleton, and they're nearby where a charge happens to be. The chlorine never picks up that negative charge. It just happens to be nearby where a negative charge is. As a result of that, it's like pulling on the bonds through the sigma skeleton and helping that charge. It never is never. There's no resonance structure. Exactly. It's never formally charged.
So it'd be like the other highly electronegative atoms.
Exactly. Oxygen will do it. Sulfur will do it. Anything that's more electronegative than carbon can help. Right? Okay. So consensus. Most acidic is top, middle, or bottom? Bottom, why?
Because if the bottom right's the weakest base, then it has to have the strongest conjugate acid.
Okay, that's one good way of saying it. This is the weakest conjugate base. Remember the reciprocal rule. If this is my weakest conjugate base, my strongest acid will be this one. If you had to think of an analogy to this too, if this is a really happy home, this acid is just dying to go to his happy home. The acid, by losing that proton, you have to put in some time, effort, and work. The acid has to delocalize or lose this proton to create this negative charge. If you're going to a really stable home, better acid. The acid is more likely to lose that proton because there's really less cost in doing it. energetically, it's going to a stable state. Losing that proton is no big deal. So yes, this marks are more stable. The other way you can draw this, right, is if we're trying to do sort of this head-to-head, we can draw the conjugate bases we're trying to compare, put them on either side of an equilibrium, add the conjugate acids to either side, and then pick the direction of the equilibrium based on this rule. If you know you're going to a more stable state, this equilibrium, if we had an equilibrium that was comparing this guy versus this guy, if those were on opposite sides of some equilibrium arrow, it must favor this bottom corner. That is the more stable one, so the equilibrium will move in that direction, away from the conjugate acid side of it. Okay? Make sense? All right, let's go back now to this problem. So this is a head-to-head. Remember, the way we just approach this is first, draw the mechanism. Look at the charged species. Figure out which is more stable. Pick the direction, who's strong and who's weak. So, draw the mechanism. Who's my acid and who's my base? If I labeled these guys A and B, or 1 and 2, going from left to right, which is acid and which is base? A is acid or B is acid? Okay, why is A the acid? Yeah, you've got this extra proton that you're going to lose as you connect to its conjugate base. All right, so this is my acid. This is my base. How convenient. All right, now that I've picked acid and base, the next thing I need to do to complete the mechanism, every mechanism is going to be the base. Wherever I'm forming my bond, that's the center that I need to start my arrows. I'm going to create a new bond to my proton, and I'm breaking a bond to this nitrogen. Quick question. I've chosen to highlight yanking off this proton. If you look at the product, this NH is kind of pointing off to that direction. Is this a problem? Who says yes, it's a problem? Okay, who says no, it's not a problem? It isn't. The only reason, again, if you want to be formal, there's nothing wrong with saying, oh, wait, look, the product has the NH going off to the right, so I better pick the NH that's on the left-hand side, just sort of mapping those things. Nothing wrong with that. As it turns out, protons are jumpy little guys. They will move as they need to as you go through these deprotonations. Now, again, advanced stuff, what we start doing with chirality and chiral bases, yes, it absolutely matters. In a case like this one, because of the symmetry of the molecule, I could take that guy right here. What would happen if I picked it up and turned it over? Same molecule? Yep. That's why. There is no difference in this molecule. If I were to pick it up and plop it down, this is my right hand, it's still my right hand. Drawing the hydrogen to the right or to the left is just an optical image of a symmetric molecule. Okay, that's why I just wanted to put that in. All right, so that's my arrows. Identify the two charged species. That one. And this one. Which is more stable? So now let's go through our rank. What makes them the same? What makes them different? We're talking about an NH2 plus and an NH2 plus. Can I use electronegativity? Not the way it's set up. Polarizability? No. What next? Resonance? Okay, what about induction? Okay, so induction, maybe. Let's look at the two. Okay, why would you say induction? What makes these two different by induction? Yeah?
The oxygen's more electronegative than the nitrogen.
Okay, oxygen is more electronegative than nitrogen. Cool, that's true. Is there resonance structures in this?
Yeah.
Yes. Okay, so we have this head-to-head. There's two things that we could evaluate in this compound. We have, you're right, this is more electronegative, this is less electronegative. And if you stop there and say that, what would our rule tell us? Nitrogen is less electronegative, oxygen is more electronegative, so if we're going to apply that, what's your decision? Who's more stable, left or right? Okay, so left is more stable. Why? It's more electronegative, right? But what type of charge is that?
Positive charge.
Yeah, positive charge. So if I had to make that call, if I said, look, I believe oxygen being more electronegative is the thing that I'm going to hold on to, I'm dealing with a positive charge, what would I expect? Yeah, it should go right. My expectation would be it should move to the right because oxygen is more electronegative. I have a positive charge. That's a bad thing, right? So from that argument, I'd say it moves away from the left towards the right. That would be how I would call it. I would argue applying induction in this way is incorrect. Now, what was the formal, fundamental rule of induction? Does the atom that is helping, the electronegative atom, does it ever be charged itself? Remember, the coach, hands folded, you can do this, I'm not actually helping. No money in, no help, just moral support. Let's draw the resonance structure. If I take this one, and I draw its resonance contributor, I would draw it lone pair sigma pi, or lone pair sigma charge, right? Or sorry, pi sigma charge or pi sigma lone pair. If I do this, its resonance contributor will be oxygen, nitrogen, my two hydrogens, oxygen. So the charge species itself can delocalize this charge to actually give me back lone pair here, double bond, positive charge on oxygen. And the same thing over here. The resonance contributor here would give me back, or move the positive charge to this nitrogen. This is why it's not induction. Induction only applies if an electronegative atom is helping through the sigma skeleton, not just because it's electronegative nearby. Again, that may help a bit, but the much bigger point here is, at some point, there is a resonance contributor where oxygen will hold that charge. The formal charge can sit on oxygen. There's a delta plus on that oxygen. Same thing with a nitrogen. There's a delta plus on that nitrogen. This is resonance. Resonance will win if it's possible, and resonance wins here because not induction, charge moved. Okay, let's look at this as resonance. Now what do we say? Who wins? Do they both have the same number of resonance contributors? Yep, so we can't make a differentiation there. They both have what you see plus two more, right? Both oxygens could help or both nitrogens can help. Based on that, now we've got nitrogen with a positive versus oxygen with a positive. That's the real difference between these two. So again, if you had to decide between the two, which one of these two resonance structures is more stable? Oxygen plus or nitrogen plus? Nitrogen plus. So it still holds. What we just said about, oh, this is induction, I think that having a more electronegative is there, that is still in the same direction. The reason I want to underscore it is you'll still get the right answer, you're not thinking about the right way, and it will burn you in certain cases. If you look at this and say, nitrogen's electronegative, oxygen is more, it's nearby a positive charge, you predict the right thing because it's kind of based in the same point. The thing I'm underscoring is the mechanism why it happens is resonance, not induction, because the charge actually sits on nitrogen. Where this comes in is in degrees of how this applies. Having a nitrogen physically on an oxygen or a nitrogen, having a positive charge on nitrogen or oxygen is a much bigger deal than having an electronegative group nearby. The magnitude will surprise you in certain cases because there is resonance happening here. So the reason I want to put up time on this is to kind of help differentiate. Does that make sense? Do you see why this is not induction? This is resonance. But the predictors go both the same ways, right? You wouldn't get the wrong answer from left or right. The why is different, that's all. Okay, so now that you know about induction, look at these four. Which do you think is most stable based on what we just discussed? Yeah, as Dr. Srichak says, mutter, 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 mutter. So everybody all together. A, B, C, or D, it is C. Why do you think it's C? Perfect. So what you guys just did there is you took a basic principle on a reaction you hadn't seen, and you applied what your understanding is, right? Bromine, fluorine, chlorine. That is fundamentally what makes A, C, and D different. Who's more electronegative among them? Fluorine. Chlorine, B, versus chlorine, C, or A. We can eliminate B because why? Further away. Distance matters is one. Electronegativity, magnitude of electronegativity, is the second. Closer and more electronegative is better than further and less. Who thought it was D? Why? No, totally cool. This is the number one thing I want to dwell on. What principle are you applying for, oh, it's got to be D? Polarizability, right? You're like, oh, wow, bromine is more polarizable. And we just talked about this. Bromine is a better what? Bromine is a better what? Charge holder. It works if bromine was bromine minus. This works if it's iodine minus. Is the charge ever sitting on bromine? No, it's sitting back going, I'm electronegative. I'm just not as electronegative as fluorine. Yeah?
How do you decide if distance or electronegativity has a bigger impact?
Hard. So in the end, if we had fluorine 3 atoms away versus bromine 3 atoms away, easy. It's electronegativity. If we had fluorine 4 atoms away, but bromine 2 atoms away, I'm being a jerk in that case.
Okay.
That's hard. I don't think you can easily differentiate them. Yeah?
So it always kind of be like, for polarizability, it's better at holding the charge, but then for electronegativity, it's better at like sharing it.
Exactly. So this is where I want you to, again, clear bullet points. Electronegativity as a stabilizer, we're talking about an element that is charged, ranking between two elements, same row. Polarizability, an element that is charged, related in the same column. Resonance, the ability to spread amongst many centers. Induction, an electronegative atom that is in the vicinity of a charge. So don't call this electronegativity. That's part of the principle. This is induction. It is having an electronegative atom by. You still have to look for electronegativity. That will help you. It is not formally classed as electronegativity. Yes?
Kind of a dumb question, but how do we factor out the fact that the charge cannot be transferred to the fluorine or the ion form?
How do you make it so it cannot be? Like, how do you know the charge is not on bromine?
How can you tell that it can't go from nitrogen to the other one?
Yeah, so how you would tell, can I take this and then draw a resonance structure in any way to hop it over here? There's no pi bonds. There's no way to take this negative charge and delocalize it over this center.
So there's no pi bonds, there's always going to be no pi bonds.
Exactly. If there's no pi bonds, there's no way to move it. That's it. If there's no resonance, no way to move it. If it's nearby, it's what doing is just tugging through the sigma bonding skeleton. So the right answer will be that guy. Distance and amount. Yep.
So we can only look at polarizability when there's a resonance.
You only look at polarizability when the element that you're comparing is charged. Right? This would have to be a sulfur plus or an oxygen plus. Those are the things. Yes?
If it was positively charged on the,
Ah, yeah.
would it like
So good question. What do you think would happen here? What do you think would happen? Let's say we have oxygen plus versus oxygen plus, but I'm going to put like a bunch of fluorines right here. Top or bottom? Who is more stable? What would your expectation be? Use your logic. You've kind of broke up now. What do you think? So who votes top? Who votes bottom? Why do you think bottom is more stable?
Is there something to help with the charge?
Does fluorine help a positive charge? I put 2 fluorines that's sitting there going, come on, you can do this! And the thing's like, that's not the help I need right now. I just need a hug. This does not help you. If these guys are sitting there just tugging on you and giving this insane energy, but that's not the kind of help it needs because it's missing charge, it's negatively charged, it's positively charged, that's not going to help. This is following the same rule as if it was electronegative, right? It's the same concept of does a more electronegative atom stabilize a positive charge? No. So more stable. Cool? Yes?
What if both fluorine and bromine are having the charge? Then would you use actual negativity or?
Sorry, say it again. If both fluorine and bromine are holding the charge?
Yeah, like if they're both holding charges, would you use like a negativity or polarizability?
I cannot think of a nightmare molecule that would be possible.
No, I mean like if you're comparing like bromine minus versus like fluorine minus.
Yeah.
Then which one would be more stable?
Well, think about it. So that's just bromine minus versus fluorine minus. What do we use in that case? Our 4 rules: induction, electronegativity, resonance, polarizability. Polarizability, clear cut, right? There's no molecule I can create that would be like a bromine and a fluorine. Again, if you make a minus, that's all it is. Br minus, F minus. There's no other bonding I can do, right? This is one of the things that's good about this too. As you work through different practices, some of the nightmare scenarios are, whoa, but what about this? It's not physically possible in some cases. So just follow the procedure through, do the practice set. It will help you out a lot. Yes?
So if the fluorines were potassium, it would be better?
Oh, okay, if the fluorines were potassium, that's a whole other kettle of fish. Okay, just for a second, let me what is this bond? A carbon to potassium bond? We talked about this before. What is that? That's ionic. That's basically a mass carbon minus, right? Because they're on total sides different than the table, they're actually going to be separated. That's like sodium with a carbon nearby it. That is basically a negative charge on its own. So you'd consider this as equivalent to just lone pair negative, right? It's an ionic species. Cool? All right. So, and this is the thing we really, really drive home. This is what we talk about back to the halogens. Do not misclassify polarization, polarizability, and electronegativity. Electronegativity is basically proximity to a charge. It's considered induction if the element is never charged itself. It is fully considered electronegativity if the element holds that charge. Okay? All right. That is the end of up to midterm. That's the last component that you need. That's the cutoff component. What we're going to jump into now is perspective. So from this point forward, if you have molecular model kits, you definitely don't have one as cool as I do, but if you've got these, good idea to bring them to class. As a quick example, a very, very, very useful thing to have, let me try not to break this. Build yourself something that looks like this. A tetrahedral carbon, carbon with 4 different groups attaching to it, with 4 different colored elements attached to it. This is your basic for a 3-dimensional, fully asymmetric center. This is what we're going to use over and over again as a representation for geometry. We use this for chirality. We use this for all different measures of molecular structure and bonding. Okay? So it's a good thing to kind of have that as a template ready to go. What we're going to talk about now, remember, back to isomers. As a definition, what is an isomer? Same formula, different structure. The bonding is different, right? This is like we said, okay, my right hand versus my left hand, same bits, different arrangement of those bits, right? Those are isomers. There's a different way, and this comes down to sort of drawing. We have, it's not quite an isomer, but sometimes as we draw structures differently, if you remember back to IUPAC, the first naming, we could look at different molecules and say, wait a minute, those are actually the same formula, same bonding, but they physically do not look the same. The presentation or geometry of the bonds as drawn in 2 dimensions look different. An example of that was sort of like our hexanes that we looked at before. When we went through IUPAC naming, we could have 2 molecules that are actually identical, same bonding, same IUPAC naming. But the representation when you come down to 2D plane can still be different. These are called conformers. The conformation is the geometry around a single bond. The reason this happens is like here we have ethane. That's what I'm trying to represent with my model kit right here. The thing about a sigma bond is they freely rotate. They're like a little pinwheel. This energy for rotation is actually very, very low. At atmospheric sort of room temperature pressure, this is happening ridiculously fast. They're pirouetting constantly. It's a very, very easy rotation. Because of that, It's sampling all of these conformations. The molecule is constantly in motion. This molecular rotation is very easy to do, and it's unique to sigma bonds. As a result of that, there's kind of different versions of how you would draw that presentation. So here in sigma bonds, we can have different conformers which come about because of a rotation around that sigma bond. So these videos you see here, these are posted in the eChirp. It allows you to sort of interact with them. Depending on how you like to sort of look at this, it's either something you can do visually in your head, or we have these sort of presentations online. What this looks like is because we have an sp3 sigma bond, there's no barrier to rotation. It can pirouette, right? And here, if these are all hydrogens on one side, all hydrogens on the other, what do you think about the relative energies of this? Is there anything that's preferential as you rotate that bond? There is slightly. If you look at this, it's very easy to rotate, but there's a bit of a barrier. And that means if you look down this bond, this here, what I'm showing you, where the hydrogens on their end are aligned, the ones up here at the front are aligned with the ones here in the back, right? This is different than that. If I rotate that front carbon by 60 degrees, what I get is this offset kind of point where now front carbons are kind of out of the way of the back carbons. If I keep rotating, what does this look like again? Same or different than my first? They're all overlapping again, other than colors, right? But if these are all hydrogen, this is the same. Then, here, here, here. What you notice is if you go around this perspective, so this is just showing that same thing in this kind of sort of off-cycle angle. This rotation, we have these two fundamental geometries you can think about. One of them, the two blue atoms we're showing here, they're aligned, they're parallel to each other, and as a result of that, all of the carbon-hydrogen bonds on the front carbon are aligned with the carbon hydrogens on the back. What I mean there is that this bond angle here and this bond angle here are right on top of each other. Versus, if I was to, again, go through that rotation again, when they're in this point here, what I just did is I've aligned this bond and this bond. They're now 180 degrees from each other. You have really two general geometries. Everything up front is aligned with each other. The bonds are overlapping versus the bonds are out of each other's way. And we have a name that goes along with those. They're called eclipsed. Eclipsed is where all of the bonds are aligned with each other if you look down the axis of the bond. And we have staggered. Staggered is where they're out of each other's way. So we call this eclipsing because this bond and this bond are right in each other's face, as is this front, this back, and this back. If you were to look at it from a different perspective, it becomes a lot more obvious. But showing it here on this flat, sort of three-dimensional geometry, eclipsing is here. Staggered, everybody else, this bond here splits the difference. It's actually bisecting the angle of these ones back here, as is the other side. Having them at this 180-degree angle allows them to kind of get each other's way. What do you think about energy? Who is higher and who is lower? Higher is eclipsed. Lower in energy is why?
The bonds are farther apart than staggered.
Yeah, bonds are farther apart. Why does that matter?
They want to be farther apart.
They want to be. Go one deeper. Why?
Because they repel each other.
They're electrons, right? If these are all electrons, what's happening is electrons, negative charge, and electrons that are negative charge are physically repelling each other just coulombically. This creates what's called strain. It is a strain that happens because what we get is actually lines on lines, bonds on bonds. And as a result of that, negative charge and negative charge will start to repel each other. Eclipsing becomes higher in energy just because of repulsion between these electrons. Thank you so much. So generally we have these 2 points. We have eclipsing and we have staggered. And the reason we break them out like this is everything that's in between those two major points. If I were to go from my eclipse structure and I just start to rotate it, so I'm starting here, I'm eclipsed, I start to rotate it in either direction. What you'll notice is this is just off that maximum. It's a little better either direction, but then I reach my staggered structure. Once I'm staggered, I'm happy, low energy. If I keep rotating, what happened? I'm now back to eclipsed, back to staggered, back to eclipsed. So they oscillate. That's why we only really have two. Threefold symmetry around that CH bond just means you have two choices. You're eclipsing or you're staggered. That's it. Staggered being lower in energy if possible. So what we now have to bring in, yes, sorry.
So why do they spin then if like it wants to stay in a staggered state?
So if you were to freeze it, make it cold enough, it would stop here.
Okay.
Think about this back to like we talked about activation energy. This is like a transition state. It's high in energy because it's passing through a maximum point of energy. It's a bit of a barrier. It's not very large. So if you have enough energy, it will spin. And you can think about it maybe not spinning freely like this. It might be geared like click, 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 right? If you cool it down enough so that the amount of energy available is no longer enough to move through that barrier, now they'll start to just kind of rock. And then as you cool it to get to absolute zero, that's it. That's all you got. But you can think about it very much like an activation barrier for the reactions we talked about. It is a barrier of energy, it's just not very large. Yep. Why are they spinning? Because the barrier for this here, that interaction, while bad, is only a couple kilocalories. They spin because when you put energy into a thing, it allows, based on entropy, it's a way of distributing energy in the molecule, right? This bond here just is some degree of freedom for it to rotate. It's a way of binning energy or holding it in a molecule, the same way a carbon-carbon bond is. Yeah?
So if I'm getting this straight, it's higher energy when
Eclipsing?
yeah, it's higher energy when it's eclipsed because the bond interactions are stronger?
Yes, they're closer to each other. The physical difference between those electrons that are in that carbon-hydrogen bond, they're in each other's face.
Okay.
That's exactly it. Yep. But it's minor. Again, we're pointing it to right now in carbon-hydrogen. This is the smallest one you can get. It's a tiny little unit of energy. To make this clearer, the type of notation we've got here is not perfectly tuned for sort of explaining this. This is where we have to bring in what's called Newman projection. Newman projection is a different way to look at three-dimensional molecules. This is where we start having the creepy head, which is looking down this bonding axis. And if you were to do that, that is the projection we would sort of say. We create a Newman projection by saying what we're trying to emphasize here is, in this Newman projection, this front carbon is this front carbon here. In behind that carbon is this guy back here. So you're looking down the bonding axis. The front carbon, the one having this circle, that circle we're representing here is the carbon atom. In behind, because it's a perspective view, behind that carbon atom is this dude. If I were to color code it, this red carbon atom right here is tucked in behind it. They're just on top of each other based on our perspective. That's why we've color coded it this way. If you notice, white is our white guy, yellow, yellow, red, red. In behind, we have blue is blue, green is green, blue is blue, and white is white. The composition matters. So from this perspective, if I was looking in the perspective here, this red head, I'm looking from left to right down this bond, and this is the Newman projection I get as a result of that, where the three elements, the yellow, red, and white, are on the front center. If I was to draw it, this is what I'm saying. I'm taking that molecule, and I'm rotating it to look down this one. That's why you get this presentation that looks like what we call this Newman structure. It's this kind of this bisected structure in this point. So practicing how we transition from 2D line bond to Newman is what we're going to have to practice through now. The important thing is every bond has a perspective view. If I look from left to right, I get this Newman structure here, where the yellow, red, and black are on the front carbon, green, blue, black on the rear. If I were to look from the opposite, now from right to left, in this blue one, now front carbon, the one that's closest to my eye, is blue, green, white. In behind now are my yellow, red, white. What's important here is yellow is not attached to the same carbon as blue. It's a composition where we're not moving bonds as we move between the two. You can think of it where the carbon in the front, if I'm the sort of red head, the carbon in the front contains my yellow, my red, my white. The carbon in the back is green, blue, that. That does not change based on perspective. It's just which geometry you're looking at from the front or from the back. So you need to be able to sort of look at these. And this is also the same thing as how we can now clearly see our eclipsing. In that staggered structure, each of those front and back bisect each other. In eclipsing, they're on top of each other. And generally, by convention, we draw it like this, where there's just a little bit of a difference in that bonding angle, so we can show what's attaching. You can actually draw them directly on top of each other like this, where the front and back are sort of like lined up, but it becomes very difficult to sort of put your atoms on. That's why usually what you get is this slight cant, because we're still trying to say content, what is on the front and what is on the back. But it's this type of structure that you can start to see very clearly why this is higher in energy. Bonds are bumping into bonds here. That's what we're trying to emphasize, is each of these is a carbon-hydrogen bond that's now bumping into or closer to the one behind it. What we can do to talk about these different structures is what's known as the dihedral angle. It is the angle made between any sort of position around this ring, a carbon-hydrogen bond that we take as a line. And we can clock this out just like the face of a clock. If this is the bond I'm looking at here, the angle I'm representing, this here, this 60 degrees, is the dihedral that's made between the carbon-hydrogen up front and a different carbon-hydrogen on the rear carbon. It's the torque or twist that exists between those two planes. Likewise, we can look at the two opposite ones here from the carbon-hydrogen at the top. Again, what we're doing for each dihedral angle is we're comparing some carbon-hydrogen bond as a plane on the front with some carbon-hydrogen bond in the back. The 180-degree dihedral is just these two positions here. We call this anti. They're the furthest away they can possibly get to each other. Now in this case, since they're all hydrogens, there's really not a lot to differentiate besides labeling those hydrogens. But as we get to bigger structures where this is not a hydrogen anymore, you can start to see there's actually differences in energy between these staggered. There can be differences where actually, if these were large groups, if these hydrogens were something else beside hydrogen, some large atom, there's actually some benefit to this specific geometry where they are 180 degrees from each other because you're putting those two large groups at the furthest they can get. If we put them in other ones, they start bumping into each other again. The dihedral angle for all of these in the front, eclipsed, is 0. They're on top of each other. The difference here, if we were to go from this front to this rear, that's just the normal bonding angle that we draw for a normal sp3 center. Now again, why does it look 120? What is the normal bonding angle for an sp3 center? From Vesper theory, it's 109.5. So why does it show up as 120? It's simpler than you think. Yeah. It's perspective, right? All we're doing is this here, this is an sp3 center. Yes, the bonding angle, if I look down the plane of the bond, is 109. But if I look at it flat, I am splitting a circle in 3 equal parts. I'm actually projecting this as a 2D projection. 120 degrees is my way of cutting down a 360-degree circle. That's it. We're not saying the bonding angle between carbon and hydrogen is 120. We're saying the dihedral angle made between a line and a line, front and back, is 120 degrees. Yes? Excuse me? Oh, the negative or positive, just the face of a clock. If you were to start here and move counterclockwise, we call these negative rotations. In this direction, they're positive rotations. So if you start from this perspective up front and we move to a negative 120, we're just going in that direction. It's the direction around the circle. That's why positive 60 is in this direction, negative 180, which also, again, corresponds to positive 180. Symmetry around a circle. That's it. Okay? So that means as we go through this rotation, this is what it looks like to sort of move through this rotation in 2D as well as around the actual structure. They move, I know it's beautifully mesmerizing, right? But this is happening all the time where you're going through this cycle. Now, what does this mean about an energy diagram? If you had to sort of pick what's going on here, which one is high and which is low? High energy is our, let's see, eclipsing. Low energy is staggered. So in each one of the eclipsing structures, same energy or different energy? They're all the same. What about staggered? Are they all the same low? So what do you expect this to look like? If I was going to graph out the energy as I go through, Yeah, this is going to start looking like. Dang it. No. Okay. We'll break there. No, I can do it. I can do it. Sorry. What's going to happen is you're going to be oscillating from high, low, high, low. The highs are all the same. The lows are all the same. The periodicity you're going to go through, though, each high and each low, what is this difference? If we're counting out the degrees, what is the difference from high to low if I'm actually rotating around this? Imagine you start eclipsing 0 degrees. If we move 60 degrees, yeah, each one of these is a 60-degree period. Up, down, each point. We're going to walk through this energy diagram as we go through next class. I'll see you guys next time. Yeah, there you go.